This is my name is Ledesma. I am a professor at La Rioja International University in Spain. And this is the name of this presentation, exploring DAG-based architecture as an alternative to blockchain for critical IoT use cases. So this research presentation discusses the use of Directed Acyclic Graphs, DAG, in place of blockchain technology for critical use cases in the Internet of Things. Well, the focus is on vaccine cold chain monitoring, where the blockchain's speed and scalability are limited. So we did a pilot project that simulated cold chain monitoring with different IoT technologies, connectivity technologies in this case. So the objective was to showcase how the DAG, this architecture, can provide low latency communication for critical IoT scenarios. In addition, because we are working on this research, there is a future work that will study IoT satellite communication to address the limitations of communication technologies used for global coverage. The content, first of all, we will see the introduction, the motivation, the critical use case that we present here, and the proposed architecture for the two different connectivities, LoRaWAN and Sigfox. Later on, we will see the coordination with pharmaceutical companies, because this is critical to deploy this kind of solutions in the next future. And finally, we will see the results of this research. Well, regarding introduction, as you probably know, blockchain is a decentralized distributed ledger technology that enables the recording, authentication, and processing of transactions and assets on a distributed ledger. It's known, of course, for its immutability, meaning that the information is stored, it cannot be modified, deleted, or altered. Also, the blockchain offers a secure and trusted environment through cryptographic encryption, making it suitable for various applications, including financial transactions, supply chains management, and more. Well, the limitation of the blockchain technology include the speed and the speed of the transactions and the scalability. The speed of transaction refers to the time it takes for transaction to be recorded and processed on the blockchain, and the scalability refers to the ability of the blockchain network to handle an increasing number of transactions without compromising its performance. Well, this limitation can impact the efficiency and real-time capabilities of critical IoT use cases, such as monitoring the vaccine cold chain that we will show here. Well, the motivation, the overview of the pilot project focuses on analyzing the speed of the DAG, the Directed Acyclic Graph, architecture as an alternative to blockchain for critical use cases. The main goal here in this pilot is to simulate the monitoring of the vaccine cold chain and record temperatures and alarms using the DAG architecture. This pilot project permits, we were able to see or to make an analysis of the speed of the DAG-based architecture. The focus is on analyzing the speed and efficiency of this architecture in handling real-time data recording, particularly in scenarios such as the monitoring vaccine cold chain that we saw here. The objective. The primary objective of the pilot project is to simulate the monitoring, as I mentioned before, of the vaccine cold chain, because we suppose the vaccine cold chain is of course a critical use case. Specifically, focusing on recording temperatures and alarms in this DAG. And this simulation is crucial for evaluating the capability of the DAG to handle critical IoT applications where real-time data real-time data recording is essential for ensuring the integrity and safety of the monitoring items, such as, of course, the vaccines. Well, their importance. Real-time data recording holds significant importance for critical IoT application, especially in scenarios like monitoring the vaccine cold chain. In such cases, the ability to capture and record data in real time is crucial for immediate response and intervention to prevent any potential risks in the monitored environment. So this real-time capability is essential for maintaining the integrity and safety of sensitive products such as vaccines through their storage and transportation, because these two states are the more critical, the storage and transportation of these vaccines. Well, historically, the control and monitoring of the cold chain have been carried out manually without significant change in the last 30, 40 years. Traditional methods involved in using labels with chemical reagents or thermometers to record the break in the cold chain. However, the reading or verification of these records was always carried out manually. This manual process made it impossible to verify whether the cold chain had been broken until the vaccines arrived at the health center, vaccination center or hospital, without having the possibility of checking the temperature recorded through the entire chain. Real-time monitoring of the temperature analysis in the cold chain of vaccine is crucial to prevent breaks in the cold chain. It's essential to have visibility of the temperature in real time in this case, as well as alarms that indicate an excess of temperature or a break in the cold chain. This real-time monitoring allows for immediate action to be taken to avoid breaking the cold chain and discarding the monitored vaccine bat. The current limitations in the vaccine, well, the vaccine cold chain verification system needs improvement as is not connected to, doesn't provide real-time monitoring and recording of temperature or cold chain breaks. This results in a high percentage of vaccine batches being lost during the transport. So there's a high percentage of vaccine bats that are broken during the transport or storage. So therefore, we think that a more advanced and efficient system is needed to ensure the integrity of the vaccine cold chain. So here we propose the architecture for the pilot project that we designed to monitor the cold chain of vaccine using Directed Acyclic Graph and DAG. The architecture consists of several layers. It's playing a crucial role in the process of collecting, processing, displaying temperature data and alarms. So there are different different layers. Sorry. So the first layer is the physical layer. This layer houses the IoT sensors responsible for measuring the temperature inside the refrigerators or cooling boxes for the vaccines, of course. The sensors are characterized by low power consumption with ARM architecture. Utilize low power wide area networks, LP1 connectivity. This LP1 connectivity is specifically for IoT connectivity to transmit temperature data to the IoT platform periodically. Periodically it means every 5 to 10 minutes. The second layer is the IoT communications. Is responsible for transporting the data from the sensors to the IoT platform. So here, different data transport protocols are used to exchange information between the IoT platform and the sensors, depending on the IoT devices and the communication technology. Because we can choose different connectivity protocols depending on the critical use case. The next layer is the IoT platform. This layer is where the ingestion and processing of the data from the sensor installed in the vaccine refrigerators take place. And when the platform receives the temperature data from the sensor, the information is automatically recording in DAG to track the temperature recording times and also the alarms. The next layer is the DAG or IOTA tangle, because DAG is the architecture, but the name of this architecture is IOTA tangle, and serves as the DLT where the temperature sensors and alarm information are securely stored. So it's very similar to the blockchain. So both DAG and blockchain are DLT technologies. And it allows open access to pharmaceutical companies, hospitals, vaccination centers to view the real-time status of the vaccines or the cold chain. And finally, we have the business application or visualization applications. This layer consists of the software tools that enable the visualization of temperature data and allow register it in the DAG or DAG or IoT tangle. So here, each layer of the architecture is essential for ensuring the seamless collection, processing, and display of temperature data and alarms in real time or near real time, because in real time means immediately. So in this case, we propose near real time. But near real time many times is enough for critical use cases. So here we can see the physical architecture. So the architecture diagram that you can see here provides a visual representation of the system's components, and it shows how the data flows through the system from the IoT sensors to the storage of temperature data in the DAG or IoT tangle. The components of the architecture include the IoT sensors, the IoT communication, the IoT platform, IOTA, and the business application or visualization applications. The IoT sensors, this device, the temperature sensor, measure the temperature inside the refrigerators or cooling boxes and use LP1 connectivity. So under the umbrella of the LP1 connectivity, we have LoRaWAN, Sigfox, narrowband IoT, LTM. So there are many connectivity protocols under this umbrella. So LP1 connectivity permits to transmit the temperature data to the IoT platform periodically. As I mentioned before, every 5 or 10 minutes. This time is, we think that is enough, no, for this critical use case. So, as I mentioned before, the IoT communication layer is responsible for transporting the data from the sensor to the IoT platform, utilizing different data transport protocols based on the IoT device and communication technology. So we can choose, depending, as mentioned, depending on the use cases, on the use case or critical use case, we can choose different connectivity protocols. The IoT platform ingests and processes the data from the sensors, recording the temperature data and alarms in the DAG for real-time or near real-time monitoring. The DAG is where the temperature sensors and alarm information is stored, securely stored, allowing open access to view the real-time status of the vaccine or the cold chain for the users. And finally, we have here again the business application of software tools that enable the visualization of the temperature data and alarms registered in the DAG or IOTA tangle. So this architecture guarantees the temperature data is continually monitored. So the sensor provides the real-time temperature data from the refrigerators or cooling boxes, so every 5-10 minutes, depending on the use case, or yeah, in this case, for vaccine monitoring is enough 5 or 10 minutes. The IoT communication layer facilitates the transmission of real-time data from the sensor to the IoT platform. The IoT platform processes and records the real-time temperature data and alarms in the DAG for immediate access. And the DAG ensures secure and immutable storage of the real-time temperature and alarm, enabling continuous monitoring. Okay, so here in this case, because we did this, we designed this architecture, we test this design with 2 connectivities. The first one is or was with LoRaWAN connectivity. Here you can see the physical architecture of this case with LoRaWAN. So in this LoRaWAN case, in the pilot project, utilizes SLB system sensor. SLB is the sensor manufacturer, which are designed to measure the temperature inside the refrigerators or cooling boxes. And these sensors are characterized by low power consumption and REM or ARM architecture. They use LoRaWAN connectivity, of course, to transmit temperature data to the LoRaWAN gateway. The LoRaWAN gateway used in this case is from the manufacturer called Multitech. The specific model of this gateway is Conduit AP. And this gateway establishes a VPN tunnel to an instance of Microsoft Azure where the ChipStar service is located. The ChipStar service is responsible for managing the private LoRaWAN network. ChipStar is an open source LoRaWAN network server. Is an open source version, so it's free and you don't have to pay for use it. And the initial ingestion of temperature data sent by the LoRaWAN gateway is done on the ThingsBoard IoT platform. Also, we use here ThingsBoard. ThingsBoard is an open source IoT platform, the same to ChipStar. You don't have to pay for that. And this platform, instead of storing the data internally, the temperature data collected from the sensor is loaded through a REST API to the DAG for real-time access. So each sensor's temperature data is saved as a transaction in the DAG with a value 0. And this transaction includes a message field of the transaction that is used to store the value for the temperature measured by the sensors. So once the information is stored in the DAG, it becomes immediately accessible to hospital, vaccination centers, pharmaceutical companies, or patients. The other case that we did was with Sigfox connectivity. In this case, the focus was on using Sigfox connectivity technology to monitor the basic cold chain. So we replaced LoRaWAN, and in this case, the previous case was with LoRaWAN, and in this case is with Sigfox connectivity, just to compare, both connectivities in this architecture. So this involved using SLB systems temperature sensor from the same manufacturer that we use for LoRaWAN connectivity, but in this case, the sensor use Sigfox connectivity to transmit the temperature data of the vaccines or refrigerators. And the goal was to ensure real-time monitoring and recording of temperature data to address the critical need for maintaining the cold chain integrity. And the Sigfox connectivity technology provides low power weight data network solution for transmitting small amounts of data over long distances. In the pilot project, the SLB IoT site hosted in a public cloud in Germany was used as the IoT platform. In the previous case, with LoRaWAN, we use ThingsBoard IoT platform, and in this case, we use SLB IoT platform or IoT site platform. So also we compare in these two use cases, we use different connectivity and different IoT platform. So this platform integrated with the Sigfox backend to collect the temperature data transmitted by the sensor using Sigfox connectivity. So similar to the LoRaWAN case, the IoT platform processed and immediately uploaded to the DAG for real-time updates. This involved performing a transaction in the DAG where the temperature temperature data was stored in the corresponding address for the sensor. So these addresses are in the DLG because it's basically it's a DLT like a blockchain. So when this information is stored in this address, this information, the temperature of the vaccines. In this moment, the hospitals, the vaccination center will be able to access to this information to see what's happening with the vaccine and also with the cold chain of these vaccines. Also, it's important to consider the coordination with pharmaceutical companies because this solution is important because you don't want to modify the way that this pharmaceutical companies works with the vaccine. So the good thing of this solution is that it's very transparent. So the pharmaceutical companies don't have to modify the process to transport or to store the vaccines during the chain. So in this case, an effective coordination with pharmaceutical companies and healthcare teams is essential for the successful implementation operation of the cold chain monitoring solution, right? So it involves aligning efforts and establishing communication channels to ensure seamless management of the vaccine cold chain. So it's basically it's really important because the idea is to deploy these kind of solutions in the vaccine transportation. So here the pharmaceutical companies play a crucial role in integrating IoT temperature sensor into refrigeration system and generating QR codes for tracking temperature data. So this is important because with your smartphone you can read the QR codes on the refrigerator or also in the vaccine. So when you read the QR codes, immediately you can see the temperature of the refrigerator or the vaccine. You can read it in real time or near real time with these QR codes. So the implementation of the cold chain monitoring solution minimally impacts the operational process of the vaccine transport and storage. As I mentioned before, the implementation is very easy. And it focuses on integrating IoT technologies to enhance monitoring and traceability without requiring extensive modification or to existing logistic operation. So as I mentioned, this solution is very easy to deploy and also is transparent. So they don't have to modify any or they don't have to modify anything in the operational way to transport these vaccines. Finally, here we have the results of this research. The pilot project aimed to analyze the feasibility of monitoring the cold chain of vaccine using DLT based on Directed Acyclic Graph, DAG. And the results showed that the time taken to register temperature data or launch in the DAG is less than 5 seconds from either the LoRaWAN or Sigfox connectivity. So below 5 seconds, you can register all this information in the DAG. So it's almost or near real time. So 5 seconds is enough. So you can register all this information in 5 seconds or below 5 seconds. So the statistical analysis focused on evaluating the time delays in the two communication protocols, Sigfox and LoRaWAN. And the analysis includes measuring the minimum and maximum time delays, the range of the time delays, the mode. The mode is the most frequent value, mean, median, variance, standard deviation, and asymmetry of the data distribution for both protocols. This analysis of time delays in Sigfox and LoRaWAN communication protocol was visually represented in a probability distribution chart, you can see here. And this chart provides a graphical representation of the data recording time in the DLT using Sigfox or LoRaWAN, allowing for a clear visualization of the distribution and characteristics of the time delay data for each protocol. So in summary, the results and statistical analysis from the pilot project provide a valuable insight into the performance and characteristics of the communication protocols, contributing to the evaluation of the feasibility and effectiveness of using DAG for monitoring the cold chain of vaccine. So this is the summary, but the future works or the next months, we have already started on working in this research, but using no LoRaWAN or Sigfox connectivity. The next step is to evaluate satellite connectivity, because of course when you transport the vaccines in big cities, and it's very easy to find cellular connectivity, but when you go to in Africa or in remote areas, it's very difficult to monitor the vaccine, but using cellular connectivity, because in many cases there is not connectivity, so cellular connectivity. So we are analyzing to use or to check satellite connectivity for these use cases, and also for IoT, for critical IoT use cases. So we are working on this research, but with this satellite connectivity. That's it. So thank you very much. You can see here my contact details if you need more information, and that's it. Thank you very much.